Should I share my screen already?
I think it's a good idea. Who is the chair of the session?
I'm sharing it.
Yeah, then probably you can ask him to share the screen and check those things.
Yeah.
Is it working?
Yes, I can see it.
Okay.
Hi, Kanika. So welcome everybody for the second session of the penultimate day. So this will be chaired by Kanika. Maybe we wait for 1 or 2 minutes because the last session got delayed a little bit. So maybe it will take some. Maybe you can give 4:30 plus 1 minute at least. Then you can start.
Okay.
Check.
3 minutes from now.
Sure.
Hi, Sukumar.
I think you are muted, Professor Adhikari. Shauli, can we start? Purushottam?
Yeah, it's your problem. I think we can start.
Okay, so will you start the recording or I can do that also, right? Okay. Good afternoon, everyone. Welcome. Hello, everyone, and good afternoon or good evening, based on where you are. Welcome to the second session for today. Our first speaker is Professor Shalom Eliyahu from Université du Littoral, Côte d'Opale, Cali. He will talk to us about 2 applications of Macaulay's theorem to additive combinatorics.
Thank you very much, Kanika. I'd like to thank first the organizers for setting up this very interesting conference and for inviting me to speak here. You see, I put this background, this picture I took when I was visiting Chennai 3 years ago. It's this amazing site at Mahabalipuram, about 50 kilometers from Chennai. Okay, so I put this background in order to feel a bit closer to the place. So I speak about two applications of Macaulay theorem to additive combinatorics. Let's see. Yeah, so very briefly what this talk is about. So there is a classical theorem in commutative algebra due to Macaulay in 1927, which characterizes the Hilbert functions of standard graded algebras. I will explain all that in the talk. And in particular, it gives upper bounds on the growth of the dimension of the pieces of each piece of degree I. And in fact, it turns out that it is a very powerful tool in additive combinatorics, but this has just been noticed recently. And in this talk, I will give two, what I think are the first two applications of Macaulay theorem to additive combinatorics. So one is on Wilf's conjecture concerning numerical semigroups. And I think I made a mistake. It's 1978. It's a conjecture from 1978 on numerical semigroups, which I will explain. And the second application is a very recent one on the growth of iterated subset. This is joint work with Ishita Mazumdar, who is, by the way, a mathematical granddaughter of Balu. So this is very appropriate. And more applications will come soon. I will just show the potential of this tool, which had been overlooked, at least for additive combinatorics. Of course, it's a classical result widely used in commutative algebra and algebraic geometry, but as far as additive combinatorics is concerned, I will show the first two applications, or what are apparently the first two applications. So let me start by explaining what Macaulay's theorem is. So first of all, a standard graded algebra is just a graded algebra. Standard means it is generated in degree 1, and the piece of degree 0 is a field. And so you have this relation, because Ri is just, in fact, R1 to the power I. So equivalently, it is simply, you take the polynomial algebra with its standard grading, where each variable has degree 1, and you take the quotient by a homogeneous ideal. And this is equivalent. And so now you see Ri is the homogeneous piece of degree I. It is a finite dimensional vector space over K. And so of course you want to measure the dimension of that piece. And that is the Hilbert function of the graded algebra. It's a numerical function which for each non-negative integer I gives you the dimension of Ri, the piece of degree I in your algebra, graded algebra R. Oops. So there's a natural question: what characterizes such numerical functions? And amazingly, there's this theorem by Macaulay which gives a complete characterization. So here is an example of what it says. Assume the piece of degree, the piece of degree 1 is of dimension n. Then, of course, the piece of degree 2 is of dimension at most the binomial n+1/2, of course, and this is attained, equality is attained in the case of the polynomial algebra on n variables. And so another way of writing this, if D1 is the binomial N1, then D2 is bounded above by n+1 and 1+1. Yes, 1+1 is 2. Okay, and so I need to speak about the binomial representation to state Macaulay's theorem. So fix a positive integer I. And now for any given I, so for any integer, positive integer A, there's a unique expression of A as a sum of I binomials, where downstairs you have I-1 up to 1. And upstairs in the binomials, you have a strictly decreasing sequence of integers. The last one may be 0. So this is unique. And then, since this is unique, then now you take this unique expression, and on top, in each summand you add 1, on the bottom you add 1, and this new sum of binomials you denote it this way. And we need this expression to state Macaulay's theorem. So before, here's an example. So you fix I equals 5. And as A, let me take A equals 100. This is an example which will come often in the talk. So I fix I equals 5. I take A equals 100. Then what is the unique expression of 100 as a sum of 5 binomials with so-called denominators 5, 4, 3, 2, 1? Here it is. In fact, 8, 5 is the largest binomial with 5 on the bottom, which is less than or equal to 100. You take the difference and you switch to I equals 4, and it gives you that. So producing this unique expression is easy. And then, so using this notation, so 105, you simply add to each summand on the top and on the bottom +1. So this is 96 plus 85 plus 54 plus 43 plus 32. And when you sum it, you get 152. As I said, it will come often in the talk, so remember that. If you start with 100 and take the 5th binomial representation, then this object is 152. Okay, so here is Macaulay's theorem. So take a standard graded algebra over a field K with Hilbert function di. Then for all I, the piece of degree I plus 1 is bounded above by this binomial manipulation. So it gives an upper bound for the piece of degree I plus 1 in terms of the dimension of the piece of degree I. And that's not finished. Conversely, any numerical function satisfying these inequalities for all I is actually the Hilbert function of some standard graded algebra over K. So this is if and only if, and this is very interesting. So here's an example. Assume your standard graded algebra in degree 5 has dimension 100, which means for its Hilbert function d5, it's 100. So Macaulay's theorem will give an upper bound on the dimension of the piece of degree 6, namely that. Now you remember from the previous slides, when D5 is 100, this gives you 152. And so by Macaulay, the dimension of the piece of degree 6 is at most 152. So here is a condensed version. It's a bit difficult to manipulate all those binomials. So here's a slightly weaker version, but which makes combinatorial application simpler. And take a standard graded algebra with Hilbert function di, fix I a positive integer. And now you take x, the unique real number greater than or equal to I minus 1, such that you write di as this generalized binomial. Then di plus 1 is bounded above by binomial x plus 1, I plus 1. So you see here, x is a real number, is no longer an integer. So you replace the sum of binomials by a single binomial where x is now a real number. It exists, it's unique. And you see now this is much simpler to use because you only have to deal with a single binomial. So incidentally, so in fact, for Wilf's conjecture that I will speak about in a few minutes, well, at some point I understood that Macaulay theorem could be useful, but it was a bit difficult to deal with so many summands. So I formulated this condensed version, which looks like earlier condensed version of other combinatorial theorems by Lovash and others, but this was not known. So, and when I got it, in fact, I got it for combinatorial application, but it paid back somehow because it gave this average of the Hilbert function for any standard graded algebra, which was not known. So this is a pure statement in commutative algebra, and this version, the condensed version, paid back somehow to commutative algebra by giving this lower bound on the average of the first term of the Hilbert function. Anyway, so let me speak about some sets. We've already had several talks about some sets. So you take subset of an abelian group G, and here is the sum set of A and B, the sum of all elements of one element from capital A, one element from capital B. And in particular, if A equals B, you can speak of 2A, which is A plus A, and more generally of HA, which is the H-fold iterated subset of A. And of course, one very important question, if A is finite, how does the sequence of cardinalities of those iterated subsets evolve? And in fact, we can apply Macaulay's theorem to that context. And in order to do that, we construct a graded algebra depending on the finite subset A, and with the property that it's for all H, its piece of dimension H, its piece of degree H, sorry, the dimension is exactly the cardinality of the H-fold iterated subset. And so let me sorry, I want to construct an algebra array with this property here. So this is described in the next slide. So first of all, so you take a field and you consider the group algebra of the abelian group G over K. So what is a canonical K basis as a vector space? Well, you have one basis element per element of the group. Of course, the product of two such symbols reflects the sum in the group. And now you take the one variable polynomial algebra over this group algebra, call it S. A canonical K basis, of course, is all powers of X times one of the basis symbol of K of G. The product of two such elements, of course, well, on the level of T, it's as here, and on the level of X is what you expect. And here T is considered to have degree 0. So the degree of such a basis element is just the exponent of X for all G. And thus, so this is a graded K algebra. Of course, S0 is K. And sorry, S0 is Kg. And so for all I, Si is a K vector space with basis Tg xi, where G runs through capital G. And now, so we are still in the way of constructing our algebra array. It's in the next slide. So now you call A1, An the elements of your finite set A. And now array, you take the K subalgebra of S spanned by these elements of degree 1, Ta1x, Ta2x, Tanx. So that is array is subalgebra of S generated in degree 1 by Ta1x, Ta2x, Tanx. That's the algebra. And now, of course, it is standard since it is generated in degree 1. What is the piece of degree I? Well, degree I is just governed by the exponent of X. And how do you reach I here? Well, you have to take I elements here and take their product. And so on the level of T, what you will get is an element in the ith iterated subset of A. So that's the K vector space basis. So for instance, you see R2, what is a basis for R2? You have to take the product of two such elements. So this is TAI plus TAJ x squared. And so hence this algebra array does exactly what we wanted for all H. It's a piece of a homogeneous piece of degree H. The dimension is exactly the cardinality of the H-fold subset of A. And so consequently, if we are interested to get upper bounds on the growth of these numbers, then we can get them by applying Macaulay theorem to that algebra. Okay, so we will apply twice this construction. So for the first one on Wilf's conjecture, it's about numerical semigroup. So here is, as in Olivier Ramaret talk, crash course. Here's a crash course on numerical semigroups. So there are two equivalent definitions, very different one. But first one is as cofinite submonoids of N. Submonoid, it means, so it's a subset of N. It is stable under addition, it contains 0. And cofinite means that the complement is finite. So this is one definition. So you see it's a submonoid with finite submonoid of n with finite complement in n. The other definition is all linear combinations with non-negative integer coefficients of some fixed integers a1, an, which are globally coprime. So, for example, as a1, an takes 479 and take all linear combinations of 479 with non-negative integer coefficients. And this is, of course, stable under sum by construction. And it contains all elements greater than or equal to 11, I think. 11 is there, 10 is not there, but 11 is 4 plus 7, 12 is 4 plus 4 plus 4, 13 is 9 plus 4, 14 is 7 plus 7. Yeah, so in fact, the set contains all integers from 11 on, but of course it also contains a few smaller integers like 0, 4, 7, 8. So they were invented by Sylvester in the 19th century as a recreational problem on postage stamp or money changing problem. And then later it was studied by Weierstrass and Horwitz and Frobenius and Lapéry and so on. So they show up in several branches in algebra, in algebraic curves, in combinatorics, in number theory, more recently in coding theory, and so on. They show up in many, many places. And in fact, this is a subject which is full of open problem, despite the very, very elementary definition. So they can be arranged in a tree. The root of this tree is n, the only numerical semigroup containing all non-negative integers. This is all linear combinations of 2 and 3, so it contains 2, 3, 4, 5, 6, 7, and so on. Everything starting from 2 and 0 also. So this has exactly one gap. The only positive integer not there is 1. So you see this has 0 gaps, 1 gaps. These are the only two examples of with 2 gaps, with 3 gaps. So each level gives you the list of numerical semigroups with G gaps. This is a G's level. And this tree grows pretty fast, even though we can't prove yet that it's growing. It's an open problem since 2008. So here's some terminology to go further. So you certainly know the largest gap, the largest positive integer, not in S, is called the Frobenius number, the largest gap. The conductor is nearly the same, is the largest gap plus 1, which means that all integers starting from C are in S. This is a conductor for historical algebraic reasons or geometric reasons, the conductor of a curve. I put it in blue, you'll see later why. The multiplicity is simply the smallest non-zero element in your numerical semigroup S. P, the set of primitive elements, those non-zero elements which you cannot decompose as a sum of two smaller elements in S. So these are the minimal generators. Like in the example before, P was 4, 7, 9, the minimal generators. It's again in blue, you'll see why. And L is the left part. So the part below the conductor because, you know, starting from the conductor on, everything is in S, so it's not very interesting. What is interesting is this mixture of gaps and non-gaps between 0 and the Frobenius number. This is the left part, left with respect to the conductor. And finally, the genus, also for historical reason, is a number of gaps. Those elements, those positive integers which are not in S. And in fact, these three objects in blue are the ingredients in Wilf's conjecture. So, so here are three major open problems, but there are many more. So first, the Frobenius problem. Determine the largest gap in terms of the minimal generators. This is very difficult. Then I put those three things in blue because these are the ingredients of Wilf's conjecture, which I will describe on the next slide. And more recently, the Brassam-Ross conjecture, which relates to the growth of the tree I showed you in the last slide. But I will only describe Wilf's conjecture in the next slide. And it will, so Wilf's conjecture, the ingredients will be, so the conductor, the set of minimal generators, and the left part in this numerical semigroup. And the statement of Wilf's conjecture involving these three things is very, very simple. Here is the statement. Take a numerical semigroup, take the number of minimal generators, take the number of L of left elements, take the product, and the product should be at least the conductor. You see, this is a very simple statement. And here, by chance, the date is correct, is 1978, so more than 40 years old. And so despite the simple statement, it is still widely open. There are some extremal cases when there is only one left element, namely 0. So in that case, this means that in fact, the numerical semigroup is simply 0 union all integers starting from some m. So this is both the smallest non-zero element and the conductor at the same time. And here, as minimal generators, it is easy to see. You need to take m. M plus 1 is certainly not a multiple of m. M plus 1, m plus 2, up to 2m minus 1. So you see the number of minimal generators is m. So the number of minimal generators is m. The number of left elements is 1. And so the product is m. But here m is also the conductor. So here m equals c. So you look at the extremities of these equalities. So p times l is equal to c. Here's another example of equality, and this is 1 century before Wilf's conjecture. You take a numerical semigroup generated just by 2 coprime integers. And in that case, Sylvester proved in 1884, this is the only case where you have a really explicit formula of, well, of the conductor in terms of the minimal generators. In that case, the conductor is exactly a minus 1 times b minus 1. And you can show that the number of left elements is exactly 1/2. So you see p is 2, L is c over 2, and so the product is c again. So this is again a case of equality. So you see, it's best possible since you have equality in some cases. There are more cases of equality, but essentially this is these are the main ones. And here's a state of of the art. So some frontier cases. There are many papers about it, many particular cases, and so on. Here are sort of the frontier cases. So Sylvester proved the Wilf conjecture with 2 generators, and then 10 years after Wilf's conjecture, Froberg and colleagues, they proved the case with 3 generators. And when I'm saying it's a frontier case, it is a frontier case. It means if you take any numerical semigroup generated by 4 generators, then we don't know how to prove Wilf's conjecture for just 4 generators. This is incredible. When the number of gaps is bounded by 60, this is a huge computation, but Wilf's conjecture holds true up to that level. When the conductor is at most 3 times the smallest non-zero element, so this is, I will describe a little bit, and this I did that, and I will explain why it is important. And this is where I used Macaulay's theorem. And also when the number of generators is at least as much as 1/3/3 with graph theory. So many different methods, in fact, to do. And when the smallest non-zero element is bounded by 18, and when the number of left element is bounded by 12, many different techniques to prove particular cases. So there are many more partial results. These are essentially the frontier cases. So why is this thing important? Because of a result by Alex Zai in 2013, and this is the result of the Zai. When the number of gaps tends to infinity, when the genus tends to infinity, then in fact almost all numerical semigroups satisfy that the conductor is bounded above by 3 times the multiplicity. Almost all. It means the proportion of these guys tends to 1 when the genus goes to infinity, and hence the name generic for this case. And so here is a picture. So this is the proportion of the generic case from 40 gaps up to 60 gaps, or genus 40 to genus 60. And you see at genus 60, though, about 95% of all numerical semigroups satisfy that. And of course, the proportion tends to 1 by the theorem of Zai. So this is a generic case, and so I proved that in fact, so Wilf conjecture holds in the generic case, and hence it holds asymptotically when the genus goes to infinity. And here is a very brief sketch of the proof, which is several pages long. For simplicity, assume C is a multiple of M, so Q is at most 3. And now here's a very important object in the theory. Take the a priori set, which is all elements in the numerical semigroup from which you cannot subtract M, the smallest non-zero element. Look at the pieces of level I of the a priori set. So in fact, by the hypothesis, AI is empty when I is at least 4. So it means you have only 3 interesting subsets in the a priori set, the level 1, level 2, level 3. Now write the subset of the level 2 as binomial x2 is x real. And this is where I applied condensed Macaulay to get this upper bound in terms of the third iterated subset of the a priori set, which are still a priori numbers. And now use this inequality to show Wilf's inequality. Well, this is much longer, but this was to show you this is exactly where Macaulay condensed version was used. You see, you recognize here the growth for graded algebra. Okay, so that's one case. That's one application. The second application is much more recent, and we started developing it with Ishita Mazumdar when visiting Bangalore, ICTS Bangalore last year, just before the pandemic. Growth of iterated subset, and we hope it will be accepted one of those days. At least this year, let's hope. You take an abelian group or semi-group, take a finite subset there, again, denote HA, the iterated subset of H for the iterated subset of A. And again, how does the sequence of cardinalities of these guys grow with H? And more specifically, assume you have some information about this cardinality. What can you ever deduce about the cardinality of one step more or one step less? And there's a classical result by Pluneke in the 1970, which says that, well, if you know HA, then for the steps before IA, then here's a lower bound. IA is at least as much HA in cardinality to the power I over H. So this is a classical inequality in additive combinatorics. Okay, so let me change the slide. And in fact, you see these are inequalities for all I from 1 to H, but in fact, if you know it's true for I equals H minus 1, you recover the lower cases. So these inequalities are equivalent to the case I equals I minus 1. And so we'll concentrate on that inequality, and in fact, we'll improve it. So the proof of Pluneke was with graph theory. And in fact, we'll improve this main step with some factor theta, which is defined as follow. X is a real, H is an integer, X is a real at least as much greater than or equal to H. And theta of XH is the binomial XH to the power 1H and multiplied by H over X. And this is our result with Ishita Mazumdar. In fact, this is exactly the same inequality as Pluneke, except that we have this multiplicative factor. And what is X here? Well, is the unique real number such that HA can be described as binomial XH. And of course, this inequality would not be strengthening if we didn't know that this factor is at least 1. And of course, later on, I will show that it is strictly more than 1, of course. So here is a brief proof. So indeed, so let me go back. So you see, you have this estimate with XH. So now, thanks to the algebra, graded algebra array that I introduced a few slides before, we can say something on the piece of on H minus 1A. So using exactly condensed Macaulay gives us this upper bound on the H minus 1 fold iterated subset. And then now you do some manipulation. You see this binomial is defined as this product of fractions as usual. You isolate the term with I equals 0, which is here. And this is that. And of course, this is that guy. And now you raise that to the power H. And this is the power H of that, the power H of that. And this is where we get the theta xh to the power h. And now this was raised to the power h, so we take h roots, and we get the announced strengthening. We still have to show that this number is at least 1. So let's show that in the next slide. In fact, it's equivalent to show that this is at least 1. And when you raise it to the power h, you get that expression, which is that expression. And here you can show that, in fact, in each term of the product, each term is at least 1 because of that. So that's easy enough. Now, in fact, as I said, it's not enough to know that theta is at least 1. It is not equal to 1. This is really stronger because, in fact, whenever h is at least 2 and h is larger than h, then in fact, this number is strictly larger than 1. And on the other hand, it cannot exceed 2.71. It cannot exceed E. But still, this is good enough. And the proof is just by elementary, you take. So this is E to the power h, and you use that. So in fact, it's really stronger than Pluneke. I would also like to say something. It's stronger than Pluneke in the last step, but if you go down, at each step you get a multiplicative strengthening, a multiplicative factor which improves. So in fact, if you go at the lower steps, not only h-1, but h-2, h-3, and so on. So the improvement is in fact exponential. And in fact, here is the shape of this function theta xh. Here I took x equals 1000, but the shape is really standard. It really looks like this. So this is for h running from 1 to 1000, and you see it reaches nearly E pretty quickly, and in fact it's above 2 at 500 at x over 2. So this shows that this factor is grows very quickly, in fact, in terms of x. So it's an interesting strengthening factor. Now here's a concrete example. So see what we get. Take any subset, finite subset in the integers, and the only thing you know is that the fifth iterated sum set has cardinality 100. So in that case, you apply Pluneke, and Pluneke tells you, well, okay, the fourth iterated sum set has cardinality at least 40. And the sixth one has cardinality at most 251. What about our result using Macaulay? Our result with Macaulay tells us, well, in fact, the cardinality of 4 is at least 61. And the cardinality of the sixth iterated sum set is at most 152, not 251, but 152. So indeed, you see, you take the algebra I constructed a few slides before, and so we have the dimension gives these cardinalities. And so by hypothesis, the hypothesis which is here, D5 is 100. So Macaulay implies that D6 is bounded above by that, and that it was our example in the beginning is 152. So this is how we get it. What about the lower bound for 4a? Well, it's in the next slide. It's pretty easy application of Macaulay as well. We claim that it's at least 61, as I said, and indeed assume that it's not the case. So now you write the unique fourth binomial representation of 60. Here it is. So hence 60 to the power 4 is 98. And then Macaulay would imply then that the piece of degree 5 is bounded above by 98, which is not the case because by hypothesis, this was 100, a contradiction. So this proves the lower bound, thanks to Macaulay. And so in summary, if you take any subset with fifth iterated subset has cardinality 100, then a lower bound for 4A, Pruneke gives 40. We improve that to 61. Pruneke gives 251. We improve that to 152 as an upper bound. So how good are these two bounds now? You see, so we now know that in fact Pruneke was quite far away from the correct bounds. What about those? Well, this is described in the next slide. So are they optimal? We don't know if they're optimal, but over Z, they seem to be very close to the optimal. Indeed, we found this example by computer. It has the required cardinality for the fifth iterated subset. And in this case, for 4A, we get 63, so very close to 61. And the cardinality of 6A is 145. And in fact, we conjecture that the optimal bounds are exactly those guys. And so in fact, conjecturally, the bounds we got with Macaulay, in fact, conjecturally, they are nearly optimal, you see? And so again, compare with Pruneke, which was 40, and with 6A, which was 251. I have only one remaining. So we can codify this as an extremal problem. So take an abelian group, take 3 positive integers, where M is at most the cardinality of G if G is finite. And you denote omega, let's denote omega G of HIM, which is what? Well, you take all subset of such that HA is M. And you want to minimize over all those subsets the cardinality of IA when I is small, and maximize the cardinality of IA when I is more than H. This is just a way of reformulating what we saw. So for instance, for I equals I plus H plus 1, what we saw, Pruneke gives this upper bound, and our result gives this, our result with Macaulay gives this upper bound. And the example we saw before tells when the group is Z and HIM is 5, 6, and 100. So Pruneke gives that upper bound. Our result gives that upper bound, and our conjecture is that the correct value is 145. And so here's an open problem which was not really addressed in the literature so far. It seems determine, at least over Z, this function. Okay, so thank you everybody for your attention, and of course, happy birthday, Balu.
Thank you very much for a great talk. Let's clap. If anyone has any questions, please unmute yourself and ask. Any questions or comments? Okay, in that case, let's thank the speaker again.
Thank you.
And our next talk will resume at 5:30, so in 8 minutes from now. Okay, so Professor Koblitz, would you like to share your screen and just check if everything is working okay?
Is that clear? Is that okay?
Yes, it's quite clear.
And is my voice volume okay?
Yeah, it's all right. There is some other sound.
There's no sound I'm hearing here. Do you know what the sound is?
Hi, Koblitz.
Hi, Balu.
Hi.
How are you doing?
Fine.
It's good to see you after all these years.
Exactly. Yeah, now that after my daughter moved, I didn't come to that side at all.
Uh-huh. You visited Seattle a long time ago, is it?
Long time
years
ago. When my daughter was there, yes.
Yeah. When was that?
Maybe 5-6 years back.
Uh-huh.
And now she has moved to Stony Brook.
Uh-huh. She's in computer science, right?
Yeah, exactly.
So is there a problem with the sound quality?
No, your voice is quite clear. There is some background sound I'm hearing, but I think it could be just, I don't know, like from nature or something.
Okay, it might be our heating system. I'll turn that. I'll see if I can.
I hope you won't be cold because of that.
No, it won't get that cold in the course of an hour. I don't know if that will help or not.
Yeah, maybe in a few seconds we'll know. It's not very pervasive. I guess we can just continue with that because your voice is quite clear.
Okay, thank you.
Hi, Kananika. I think we have 3 minutes, right? At least 3-4 minutes.
Yes, yes. Okay, I think we'll start now. So, welcome to the second talk of the evening session. It's a great pleasure to welcome Professor Neil Koblitz. I think we all know him through one or more of his beautiful books, and his books made our graduate student life very pleasant and inspiring. Today, he will tell us what happens when the values of pure math get refracted in applied math, for better or worse.
Thank you. I'm very pleased to be speaking at this conference in honor of my friend and colleague of many years, Balu Fest. So I'll talk about both the good and the bad side of how values of logic and rigor get imported into applied mathematics. I'll start with some positive examples and then talk about the misunderstandings and foolishness that sometimes occurs. But first, before I get into the mathematics, I want to give some memories of a wonderful 2-month visit that I had at Math Sciences in Chennai in January and February of 1987, hosted by Balu. After talking about some of my fond memories of that time, I'll move on to talk about a joint result with Balu that we published somewhat later. And then a result that helps in some practical questions in elliptic cryptography. Then I'll talk about an example. I'll talk briefly about an example that goes in the other direction, in the sense that it shows how practical questions in cryptography can sometimes motivate interesting theoretical work, in this case, in analytic number theory. Then I'll move on to sort of the negative side of my talk, where I'll talk about logical flaws that arise sometimes in applied mathematics. I'll give the example of a misapplication of the uniform boundedness theorem of Osterley, and I'll talk a little bit about non-uniform algorithms. So to begin with some memories from 1987, I gave a series of talks on cryptography. And in the first talk, which was an elementary talk, I wanted to give just a simple example of decryption. And since I was in Chennai, I thought it would be nice to do this in the Tamil alphabet. Well, I only know one word in Tamil, which is Chennai. So I decided that that would be my plain text example. In other words, when you decrypt the ciphertext, you get a plain text, an ordinary word. So this is my plan, but I soon learned that the Tamil alphabet has something like 250 letters. So to give an example in that large an alphabet would be time consuming and cumbersome. And so I felt I should simplify things. So I looked at a table of the Tamil alphabet and saw that there are 30 letters that are either pure consonants or pure vowels, the 18 consonants down the first column and the 12 vowels at the top. And then I saw that the reason why the alphabet was so large is that a single letter is normally used to represent both the consonant and the following vowel sound. So I thought, well, maybe I can just use the 30 letters of pure consonants and pure vowels. So what I did was I looked at Chennai, which is in the upper left-hand corner here, and I saw the middle letter is a pure consonant, the N sound. There are only 3 letters. The letter to the left of that, that's the letter with the dot on top. And then the letter to the left is the CHE sound, and the letter to the right is the NAI sound. So I just thought, well, why don't we turn that 3-letter word into a 5-letter word by breaking up the letter to the left into the concatenation of a pure consonant for the CH and a pure vowel for the E. So I did this, I gave my example, and the ciphertext was written in this 30-letter simplified alphabet, and then the plain text that came out of the decryption was this nice Tamil word Chennai, except everybody looked at it and scratched their heads and didn't know what I was doing, what this was supposed to be, these 5 letters. And so I learned the hard way that, in fact, in Tamil, nobody would think of this sequence of 5 letters as representing anything. And you can't simply transform letters this way. So my attempt to give a simple decryption example in Tamil was a bit of a failure. So, well, after that, I think things picked up in my lectures. But I learned my lesson not to try to give an example in Tamil ever again. Okay, another memory I have is from visiting the Indian Institute of Technology right next door to Math Sciences to talk about Vietnam. Now, I just come from Vietnam, where I was heavily involved in trying to foster scientific cooperation with Vietnam, to break down the isolation that Vietnam was under at that time, the lack of contact with countries, with Western countries and other Asian countries. So I was, at any opportunity in India, I was talking about this. And in fact, I felt strongly that there should be much more South-South cooperation between India and Vietnam. And so I was talking a lot about this. And then I met some faculty from IIT from next door who came over to Math Sciences to attend seminars and talk to people. And they invited me to give a talk on a little bit on the history of Vietnam, which their students didn't know anything about. They were quite concerned because they felt that many of their students had a type of mindless veneration of the United States. You know, someone from the American consulate in Chennai had visited recently and been received with open arms by the students who didn't ask any hard questions. And so these faculty members wanted me to come and provide some balance, that is to talk a little bit about the negative side of America's role in the world, of which Vietnam is a prime example. And so I talked about the history of Vietnam and about science and mathematics in Vietnam, and had a very nice visit to IIT. In connection with that, some graduate students at Math Sciences who were from Kerala belonged to a Science for the People organization and requested that I write an article about science in Vietnam for the magazine, the publication of their organization, which they translated into Malayalam and sent me a translation. I was very proud of this translation. Having written an article that was translated into Malayalam was very unusual. Another memory from those 2 months was going with Balu and some other people to a concert of traditional Indian music, which lasted around 3 hours without any break. Now, Americans are not used to sitting still for 3 hours, especially on a hard surface. So maybe toward the end of that, it was a little bit uncomfortable, but still, it was a beautiful experience, and I really enjoyed the concert. Then a strange memory, a strange thing we did was Balu and I went to see the dreadful American movie Rambo. Now, why did we do something like that? Well, one of the things I was going around talking about, I was complaining that it was disappointing that the movie Rambo was showing in India to full houses at that time, because it's an absolutely awful movie. It glorifies violence, it glorifies American aggression and militarism. It has racist portrayals of the Vietnamese people. And I was going around saying, well, why would India even show a movie like this? India, as I said, has a whole history, very good relations with Vietnam. And in fact, India and Vietnam share a common legacy in the 20th century of bringing imperialism to its knees. British imperialism in the case of India, and French and American imperialism in the case of Vietnam. So I didn't see why such a movie would be shown in India. My Indian friends explained to me that, well, people who go to see this movie don't care about the history or the politics of all this. They're just going to see it because it's entertaining, there's a lot of violence, special effects, adventures, and that's all that matters. So we were talking about this, and Balu and I decided as an experiment to go sit through the movie, and then after the movie, as people left, we would ask them about why they saw it, what they thought about it, and so on. Actually, Balu would ask them, because I don't know Tamil, so Balu would have to do the questioning. Well, as it turned out, this experiment was not very successful. The people leaving the movie were not eager to be interviewed about it. They were not eager to talk to Balu about their impressions. Nobody wanted to say anything. And so it was a failure as an experiment because it had a cost. The cost was that Balu and I had to sit through this movie. So in a way, it was an entertaining experience to go through all this, but we did not really learn anything about what people were thinking when they were watching this movie. And the final memory I want to share is I was jogging in those days and would jog at around 6 a.m. before the heat became too much for jogging. And at around 6 a.m. the sun was rising and it looked like this. And I don't think there's a more beautiful running route anywhere in the world than the shore by the Bay of Bengal at 6 o'clock in the morning when you see the sunrise. So it was a wonderful memory of jogging in Chennai in 1987. Okay, so now to proceed to the mathematical part of my talk. Some years later, in 1995, I again visited Math Sciences in Chennai briefly, and then several of us, Balu and I and some others from Math Sciences, went to a conference in Bangalore at the Indian Institute of Science on the subject of cryptography and computation. It was organized by Balu and Benny Madhavan, and I gave a talk there on elliptic curve cryptography. Well, in elliptic curve cryptography, we want an elliptic curve E defined over a prime field Fp that ideally has a prime number of points, say q points on it. It doesn't actually have to have a prime number of points. For purposes of cryptographic applications, it's sufficient if the group order is a very large prime times a small cofactor, like for example, twice a prime. And here, the order of the group has to belong to the Hasse interval of length 4 root p centered at p plus 1. There's another condition we also need for security, so that our crypto system is secure. Namely, we don't want the elliptic curve group to embed in the multiplicative group of a small degree extension of the finite field. That is fp to the k for k less than log squared p. In other words, we don't want this prime number of points q to divide p to the k minus 1, that is the order of the multiplicative group of that extension. We don't want that divisibility for small k. So we have two basic conditions for our elliptic curve over the prime field, that it have a prime number of points and that it does not have this divisibility. In my talk, I said that heuristically, it seems very practical to find such curves, but just using a randomized algorithm. But I thought it would be hard to prove a rigorous result, guaranteeing the probability of randomly getting such a pair consisting of a prime and an elliptic curve over the corresponding prime field with the desired properties. So that was what I suggested, that this would just be very difficult to prove this sort of thing. But right after my talk, in real time, Balu said he'd come up with an outline of a proof that could give exactly the result that I wanted. And this eventually led to a joint paper published 3 years later in the Journal of Cryptology. So here's the main theorem in that paper. Suppose we choose random pairs p comma e consisting of a prime and an elliptic curve defined over the corresponding prime field having a prime number of points, where the prime p is between m over 2 and m. And here, in practice, m would have to be very large. In cryptography, m would have to be roughly of order 2 to the 250th power. So m is a very, very large number. Then the probability that when we choose this random pair, we'll have the divisibility property that we don't want, namely the order of the points q divides p to the k minus 1 for some k less than log squared p. That probability is less than an effectively computable constant times log to the 9th m times log squared m divided by m. And in view of the magnitude of m we'd be dealing with, this is a negligible probability. Okay, just some background on this. Note that if you fix p, if instead of varying both p and e, if you choose your favorite p of the right magnitude, and then just choose variable elliptic curves, then nothing can be said about the probability that a random elliptic curve over that fixed prime field has a prime number of points, let alone anything about the divisibility property. And that's because you need to know information about primes in an interval of size 4 root x. However, if you regard both p and e as varying simultaneously and choose a random pair, then you can prove that that p is prime and a random elliptic curve over fp has prime order roughly as often as heuristics would say. The order of the elliptic curve is very roughly uniformly distributed in the Hasse interval. Not really. It's less likely to be at the ends of the Hasse interval than at the middle, but you get a pretty good approximation, assuming that it's more or less randomly distributed in an interval a little bit shrunk from the Hasse interval. And so you're basically varying two numbers and asking for both of them to be prime. So it turns out that you can get something close to what heuristics would say. And then after doing that, it remains to prove an upper bound on how often, as P and E vary, you get the divisibility property you don't want. So, so that was generally how the proof proceeded. Now, in this case, rigorous mathematics was useful in practical application, useful in elliptic curve cryptography. Well, why is it useful to have a rigorously proved result of this sort? Well, a randomized algorithm, what we want to know is that it's feasible. It's a polynomial time algorithm what we want to know is that the probability that our algorithm does not give us the information we want, namely this pair P comma E with the desired properties, that probability decreases exponentially as a function of the number of iterations of our randomized algorithm. So we'd like to know that for all practical purposes, if we just repeat it 10 or 20 times, we're virtually certain to get what we want. Before this is proved, we can say that we're virtually certain that it has this feasibility property, but that's modulo a conjecture that nobody knows how to prove. So it's much more desirable to be able to say we know with absolute certainty that it has this feasibility property. So that's the type of usefulness of having a rigorously proved result rather than some heuristics. Okay, in some cases we have the reverse influence between applied and theoretical mathematics, where a practical question motivates people to investigate a theoretical issue that they hadn't thought about before. So I want to give an example of that. Before elliptic curve cryptography, no one asked about the distribution of elliptic curves with prime group order. As I said, in elliptic curve cryptography, we're a little bit more flexible than that. It's okay to have the group order to be either prime or a prime times a small factor. Then we can still construct efficient and secure crypto systems. Well, interestingly, the analogous question about the multiplicative group of a prime field, the closely analogous question, was of great interest to mathematicians historically. The analogous question about the multiplicative group of FP asks about the distribution of P such that the group order is twice a prime, that is P minus 1 over 2 is prime. And that's the Sophie-Germain prime question, because then P minus 1 over 2 is a Sophie-Germain prime, which of course is great interest in the history of Fermat's last theorem ever since Sophie-Germain proved the first case of Fermat's last theorem for Sophie-Germain prime exponents. So it's kind of interesting that it would have been natural to ask the same question about elliptic curves or the analogous question about elliptic curves, but nobody did it until there was a practical reason for caring about that. Well, the result I'm thinking of, the work I'm thinking of, is by Kumar Murthy and a co-author Ali Murray, who wrote a paper, an application of sieve methods to elliptic curves that appeared 20 years ago in the proceedings of IndoCrypt, the cryptography conference in India. And they proved the following theorem. Now they suppose that you were interested in generating elliptic curves a little bit differently than what I described before. Instead of letting P and E vary randomly at the same time, they said, let's suppose that E is a fixed global elliptic curve, that is an elliptic curve defined over the rational numbers. And then we can get, for different P's in the range we're interested in, we can get different possibilities for an elliptic curve over Fp by reducing E modulo P. Then let n sub P denote the group order of the reduction mod P, that is the elliptic curve over Fp. They prove, assuming the generalized Riemann hypothesis, if the elliptic curve over the rationals E is not a complex multiplication curve, then for at least x over log squared x primes less than x, the mod P group order, is the group order of the curve over Fp, has at most 16 prime divisors. Now that's in the direction of what we want. That is, we'd like it to have just one prime divisor or a prime divisor times maybe a few very small primes. This doesn't give us that. And for that reason, it's not of great practical interest. Or you could use it to construct a crypto system, but the problem is that you'd have to know that the largest prime divisor is at least 2 to the 250th. So for that, you'd have to be looking at if you want to be certain using this theorem that you can efficiently find a curve in this way that has its largest prime divisor at least 2 to the 250th, you'd have to choose P to be at least 2 to the 4,000, because the largest prime divisor might have bit length just 1/16 of the bit length of P. So that could be done, but it would be a relatively inefficient crypto system. It would never be done in practice simply because it would take longer to do everything when you were working with primes that large. So in practice, we wouldn't do this, but it's in the right direction for a rigorous theorem of this form that would be used in practice. But my point in talking about this theorem and praising this theorem is not that it was something that was essential for practice, but it's a very nice result that illustrates that cryptography can have some value in motivating research into new questions in theoretical mathematics. Okay, a lot of work in cryptography relies on heuristic assumptions and empirical experimental work and is not at all rigorous. But still, notions of rigor and formal logic, when they can be brought in carefully, can be of great value. On the other hand, sometimes notions of rigor and formal logic are brought in to cryptography in papers that make claims about the relevance to cryptography to bad effect. That is, sometimes some rather foolish things are done. So I want to give a couple examples. First of all, a paper also about 20 years ago, written by Cheng and Uchiyama with the title Non-Uniform Polynomial Time Algorithm to Solve Decisional Diffie-Hellman Problem in Finite Fields Under Conjecture. So let me explain what these words mean. The decisional Diffie-Hellman problem, the Diffie-Hellman problem is a basic problem in cryptography. The decisional problem means it's a yes or no question. And the question is the following. The decisional Diffie-Hellman problem in a prime field FP asks, given a generator G of the multiplicative group and 3 elements A, B, C, is the index of C to the base G to the base of our generator equal to the product of the indices of A and B, where of course the index means an integer modulo P minus 1. So it asks, yes or no, is the index of C equal to the product of the indices of A and B? It turns out that that in certain types of cryptographic protocols, cryptographic setups, you want to know that this is a difficult problem. That is, if you choose P large enough, you can be confident that someone who's trying to attack your cryptography will not be able to solve this problem. That it's a difficult problem to solve. That's what you want to know in certain situations. So what they suggested, they said they have a certain type of algorithm to solve this problem in polynomial time. Well, their algorithm is a non-uniform algorithm and it requires a conjecture. So I want to say what that means. Well, non-uniform means that when it's a concept in theoretical computer science. It means that when you're solving the problem, you're allowed an advice string that's of polynomial size, that is, its bit length is a fixed polynomial, is bounded by a fixed polynomial function of the input length. So a reasonable size advice string that will help your algorithm solve the problem. And when you say a polynomial time non-uniform algorithm, the running time of the algorithm does not take any account of how long it might take someone in practice to find this advice string. So the advice string you just suppose you somehow have. Well, strictly speaking, the advice string has to depend only on the input length. That's not true in the Cheng and Uchiyama paper. They're using uniform in a much looser and precise sense because their advice string depends on P, not just on the input length of P. So if P has 250 bits, the advice string doesn't just depend on that, it depends on what the actual value of P is. However, it does not depend on the other input to the problem. That is, the advice string does not depend on G, A, B, or C. So it's still, it's not a trivial statement at all. Okay, so what is their conjecture and what is the advice string? Their conjecture is that there always exists an advice string of the form that they need. So this is their advice string. And let's suppose, for simplicity, that the order of the multiplicative group of the prime field is twice the Sophie Germain prime. Then their advice string in that case is an elliptic curve defined over a number field K having points of order Q also defined over K. Now, since the advice string has to be of reasonable size, that means that the number field has to be of reasonable size. It has to be describable, and the coordinate of the point of a generating point has to be describable in a polynomial number of bits. So the advice string is the description of the number field and the elliptic curve and the point of order Q. That's the advice string. Their conjecture is that such an advice string always exists. They don't have an algorithm to find it, of course, and you don't, in a non-uniform algorithm, you don't worry about that. You just assume that somehow you have this curve. But the curve has to exist, otherwise you don't have an advice string. Okay, so they conjecture that such an advice string of polynomial size in the bit length of P always exists. The author's justification for this conjecture is a uniform boundedness theorem proved by Osterley, which says that if D is a degree of a number field K, and if E is an elliptic curve over K with a point of prime order Q, then Q satisfies an exponential bound, essentially 3 to the D power. It has an exponential upper bound. This is what the authors say in their paper. Fortunately, the current research seems to indicate the maximum possible value of Q, that's what they mean by number of torsions, over a number field grows exponentially with the degree of the number field. Well, this statement is a bit confused. They're confusing an upper bound with an optimal upper bound, which in this case is quite a different thing. Well, it's certainly true that researchers could not prove a better result than Osterley's result. They could not prove a sub-exponential bound on Q. But it's also true that no family of elliptic curves was known for which Q grows faster than root D. And it was conjectured that Q satisfies a polynomial bound in D. So it was widely believed that Q is bounded from above by some polynomial in D, although nobody could prove that. So the authors seem to think that the inability to prove that something doesn't exist is good evidence that it does exist. So if you don't have a definitive proof that something doesn't exist, you might as well come up with a non-uniform algorithm that uses as its advice string the thing that they can't prove doesn't exist. So analogously in the real world, we might say that we don't have probes to go to the moons of Jupiter yet, to explore the moons of Jupiter. So we might as well conjecture that there are little green men walking across the ice fields of Ganymede. You know, why not if we can't prove that it's false? So I think few mathematicians would do this, would conjecture, for example, would make the logical leap of conjecturing that, for example, the existence of a non-trivial zero of the Riemann zeta function off the critical line, justifying the conjecture on the basis that nobody's yet proved the Riemann hypothesis. So so the argument that they thought was a strong argument for their conjecture is actually not very sensible. And concretely, one way to think of their conjecture, the elliptic curve whose existence they conjecture we can always count on, is to look at the modular curve x1 of q. Now, the modular curve x1 of q parameterizes pairs consisting of an elliptic curve E along with a point of order q. And in our case, both the elliptic curve and the point of order q have to be defined over a number field k, which means that the point on the modular curve has coordinates in k. So if the point on the modular curve has coordinates in k, then E and q are what we want. But remember that that q has to be very large. And in fact, the type of cryptosystems that are based on the decisional Diffie-Hellman problem require q to have at least 1,000 bits. So the prime order q must be at least around 2 to the 1,000th power. And the modular curve has genus of order q squared. So in a secure cryptosystem, we'd be talking about a modular curve with genus roughly 2 to the 2,000th power. And so we'd have the conjecture is that that there exists a manageably sized point on a Riemann surface that has about 2 to the 2,000 handles. So does this have any value in cryptography? I don't think so. And even if there is such a curve, such a point on the modular curve, at the very least, you'd need divine intervention to find it. So non-uniform algorithms, although they're an interesting, an important concept in theoretical computer science, from a practical standpoint, a non-uniform algorithm is not really an algorithm in the real world sense of the word algorithm, because it relies on an advice string that nobody knows how to find. Well, my co-author, Alfred Menezes, and I wrote a paper with the title Another Look at Non-Uniformity, where we criticize misconceptions about non-uniformity that are widespread among cryptographic researchers, including some of the top cryptographic researchers. So I want to give an example of another type of misimpression about logic and mathematics. Okay, now a typical theorem in cryptography, a so-called provable security theorem, would have might have the following form, and I'll explain what these words mean. If f is a collision-free hash function, then our authentication code constructed from f cannot be broken. So what does this mean? Well, a hash function is a function of messages. The input is a message, and the output is a message can be of arbitrary length, an arbitrary bit string of any length. But the hash value of it, the result of applying the function, will be a bit string of fixed length, usually 128 bits. And it's like a fingerprint of a person. It's a digital fingerprint of the message. The hash functions are used throughout cryptography. They're used in digital signatures, authentication codes, encryption, many other things. The crucial property that you want a hash function to have is this collision-free property, which means the following: that it's not feasible to find two distinct x's, x and x prime, that have the same hash value. So it's a type of one-to-one condition, but it's one-to-one in the sense of practical computation, not in the mathematical sense of one-to-one. In fact, a hash function is infinity to one, because there are infinitely many messages possible if you don't restrict the length of a message, and only finitely many hash values. So there are infinitely many messages that might give us the same f of x. But the point is that you'd never in practice be able to find x and x prime such that f of x equals f of x prime in a reasonable length of time. There's no reasonably efficient algorithm to do that. It's just an impractical task to try to find two messages with the same hash value. If the hash function does not have this property, then it's not a good hash function. So you always want to assume at least that the hash function is collision free. Okay, then the authentication code. Well, what's an authentication code? That's a protocol, meaning just a sequence of steps by various parties to the communication. So typically we call two people who are communicating Alice and Bob. So in this situation, an authentication code would be a method in the communication between Alice and Bob, whereby Alice becomes convinced that she really is communicating with Bob and not with an imposter. So it authenticates that it really is Bob at the other end. Okay. Now, the theorem, this type of theorem is a conditional theorem in a very strong sense because it doesn't assume like the Riemann hypothesis, which just about everybody believes is true. It assumes something that might be true now, but maybe won't be true in 10 years. Namely, it assumes that, that nobody's able to come up with an efficient algorithm to find F collisions. That is, your particular hash function, there's no way to just somehow find two bit strings that will produce the same result. It might be a very plausible assumption, but it's still a very strong assumption. The conclusion is also strong. It says that no one can develop an efficient algorithm to break the code, which in this case means no one can imposter somebody else and falsely convince Alice that they're Bob. So it has a strong assumption and a strong conclusion. Generally, proofs of security have this form. They're theorems of the form P implies Q. They're conditional theorems, where P is the assumption that the attacker cannot feasibly complete a certain computational task, such as factoring a large integer if you're using the RSA crypto system, or finding a hash function collision if you're using a system that needs a good hash function. And Q is a conclusion that the same attacker won't be able to break our crypto system by whatever we consider to be the type of break of the crypto system we're concerned about. Access to a restricted resource that they're not supposed to have, retrieving a secret key, being an imposter, falsely convincing Alice that they're Bob, this type of thing. That's the conclusion, that they won't be able to do that. Okay, so my example of a very unfortunate attempt to apply logic to cryptography comes from notes for a course at MIT given by two top cryptographic researchers, Mihir Bellari, who has a phenomenally high H number. He's probably the most cited researcher in all of cryptography, and Shafi Goldwasser, who won the Turing Award, which is sometimes called the Nobel Prize of Computer Science. So this is what they wrote for their students. They wrote, clearly the non-uniform adversary is stronger than the uniform one. Thus, to prove that something is secure, that is a provable security theorem, even in the presence of a non-uniform adversary, is a better result than only proving it is secure in the presence of a uniform adversary. So if you can prove that an adversary who has access to advice strings can't break your system, that's better than proving that an ordinary adversary can't break your system. Well, you see there's a logical problem here. The logical problem is that the theorem has the form P implies Q. And your adversary is the same adversary for P as for Q. You assume that this adversary, however you're imagining the adversary, you're assuming they cannot solve a certain computational problem, and you're concluding that they cannot break your system. So if you assume a stronger adversary, that means you have a stronger hypothesis and a stronger conclusion. And when you have a stronger hypothesis and a stronger conclusion, your theorem is not stronger. It's not weaker either, it's just incomparable. So there was a kind of fundamental logical error here. And because of that, because of this type of misunderstanding, it actually led Bellari to make a major blunder in a paper that was published in the Proceedings of Crypto 2005. Crypto is the most prestigious annual cryptography conference. This mistake by Bellari went undiscovered for 7 years, and then Alfred Menezes and I noticed it in 2012. If you're interested in details, all of our papers on criticizing the misuse of mathematical proofs in cryptography can be found at anotherlook.ca. Okay, so now, given all the misunderstanding and misuse of theoretical mathematics that occurs not only in cryptography, but in many other areas of science and the non-sciences especially, what is to be done? Well, what can be done about this? I want to give an example of a very small thing that I did just this past term. Now, this is small. It's not a major contribution to anything, and it's not something that Vladimir Lenin would have been impressed by. But I gave a seminar, a small seminar in public writing to our undergraduate students in our university honors program with the title Math That Lies, Communicating Why Some Quantitative Arguments Are Misleading or Bogus. This was a 5-credit seminar for honors program students with enrollment limited to 12. I had 11 students. By public writing, we mean writing that's accessible to the public with clear, brief explanations without jargon, technical words, or acronyms. The setup of the seminar was each week, the students, half of the students were writers, half of the students were editors, were peer editors who would help the writers improve their writing. The students would write a first version that their editor would edit, then they write a second version, and then the seminar would meet, and everybody in the seminar, the 3-hour seminar, everyone would have a chance to comment on all the writing for the week. After that, the assignments were not long. They were between 250 and 1,000 words. After that, I would also send my corrections and comments to each writer, and then they'd write a final version. So it went through really extensive editing and feedback. The students were assigned various readings. Among the case studies I had the students write about, one was David Lee's formula, often called, sometimes called the formula that killed Wall Street in 2008. This, David Lee gave what turned out to be a ridiculously over-optimistic approach to estimating the probability that a large set of loans will default at once. His formula was seized upon by Wall Street to justify its reckless investment practices in so-called collateralized debt obligations, which included packages of large numbers of loans, often home mortgages. And this a reckless practice on Wall Street that involved literally trillions of dollars was what precipitated the financial collapse of 2008. So certainly a good example of the misuse of mathematics. Another example comes from my own university, the Institute for Health Metrics and Evaluation, which became very well known a year ago in the early weeks of the COVID-19 pandemic, because it had super optimistic projections for the total number of US deaths that were likely to occur in the course of the pandemic. They estimated a total, at first, their earliest estimates during the crucial early weeks of the pandemic when people were deciding what should be done, their estimate was 60,000 deaths, which didn't seem so bad because 3 years previously, we had an ordinary flu season that had very close to that number of deaths. So it was an optimistic prediction. Now, in fact, the current number of deaths that have been recorded are around 536,000 deaths, and it's estimated that before this is all over, the deaths will go above 600,000. Disproportionately many in the US compared to the rest of the world. We have around 20% of the world total of COVID deaths, although the US has less than 5% of the world's population. So their estimate using mathematical modeling in work done largely by applied mathematicians using mathematical models, their estimate was off by a factor of at least 10. Their prediction was seized upon by the Trump administration to justify its refusal to take the pandemic seriously in those crucial first weeks of the pandemic in February and March, or in February and March of last year, or to take appropriate measures. Okay, so my hope is that given this type of background of how quantitative arguments, mathematical modeling, and so on are misused, my hope is that some of the students who take my seminar and other seminars that are being given that are like it about public writing, that these students will become effective writers who can help educate the public and expose quantitative misinformation that gets misused by politicians to advance some ill-considered policies and by commercial interests to scam people. Okay, so that's my hope anyway. I want to conclude with a recommendation of 2 books, both of them actually written by number theorists that relate to what I'm talking about. One book by Susan Landau, who received her PhD from MIT under the direction of Gary Miller. She wrote a book called People Count, Contact Tracing Apps in Public Health, where she warns about dangers that are likely to result from smartphone applications that implement contact tracing in epidemics like COVID. And these applications use cryptography in essential ways, and they're proposed by cryptographers who did not, for the most part, investigate the human dimensions of what they're proposing. So she, for the first time, wrote a book about all this, about the human dimensions and some of the dangers of unfairness toward the poor, toward racial minorities, and so on. Her book's coming out within a month. Another book, which I strongly recommend, is by Kathy O'Neill, who got her PhD from Harvard under the direction of Barry Mazur. She wrote a book called Weapons of Mass Destruction. The title is supposed to be a play on words, supposed to bring to mind the term weapons of mass destruction that very familiar to us about 20 years ago when the Bush administration was spreading disinformation about Iraq that supposedly had a huge amount of weapons of mass destruction. And the disinformation was used to justify the invasion of Iraq. So anyway, she's using this title to suggest that big data algorithms are dangerous, that the many big data algorithms involve abuses of people and scale up a lot of human fallacies, biases, and so on. And again, that in practice, these sort of mathematical algorithms used in big data science very often result in discrimination against the poor or against racial minorities, types of surveillance that should be unacceptable, and so on. So she gives a lot of detailed examples. Faulty evaluation of teachers. It's especially a big problem in the United States now. There are many really vivid examples of misuse of big data. So that also very much relates to what I've been talking about. Okay, so in conclusion, I want to wish Balu health and happiness on the occasion of the 70th birthday, and thank you for your attention.
Thank you for a very informative talk. Let's clap. Any questions?
Yes, maybe one small question if you...
Yes, please go ahead.
Yes, Neil, you mentioned heuristics about polynomial bounds for torsion of ellipticals, uniform polynomial bounds. Isn't it true that known result of Silverman and Henry maybe would tell that the Massor-Osterley conjecture would imply such a bound?
Pardon me, what conjecture?
The master of Starley conjecture, the ABC conjecture.
I don't really know. I haven't kept up with the most recent work on that. So I don't know whether that conjecture implies the conjecture about the polynomial bound. The conjecture about the polynomial bound on Q goes back quite far, I think to the 1980s.
Yeah. Because in my memory, they had a bound which was polynomial, the what they call the spiral ratio.
I see, okay. Yeah, you're probably right. I mean, I'm just not familiar with that. Yeah, thank you.
Any other questions? Okay, so maybe I will ask a question. So among the examples that you gave us towards the end, one was about this study from your university about COVID data, which did not turn out to be true. And we saw a lot of such studies and models which went horribly wrong. So do you think, I mean, did COVID-19 modeling pose any unique challenges for which the study of previous epidemic outbreaks did not already provide us with tools?
Well, my impression was that the modeling done by this IHME, the Institute for Health Metrics and Evaluation, suffered from a problem that many of the other models did not. Around the same time, almost exactly the same time in mid-March, there was a model developed by the Imperial College London that predicted 480,000 US deaths. And this model made the front page of the New York Times. It was a model that I believed at the time. They were assuming that the US on a federal level would not take adequate measures, would not take appropriate measures, and they were predicting what that would result with. And of course, that's exactly what happened. The number of deaths is greater than that, but not by at least they have the right order of magnitude. I think the difference is that the IHME model was done primarily by applied mathematicians, essentially using curve fitting. They took data from mainly from Wuhan, maybe a little bit from Italy, from the very early time, the very early weeks, and assumed that the pandemic would grow exponentially at first, then level off, then decrease exponentially, more or less symmetric way. So they made various assumptions about the type of curve, and then they just fit the data that was available to that curve. Now, what they did not do, for the most part, at that time, later on they improved. Later on they started to develop realistic models, much later when it was too late. But at first, what they did not do was take into account the human side of this. For example, information about mobility of the population, about social customs, things that people are likely to do, events that are likely to become super spreaders, and so on. They just ignored anything related to human behavior and just regarded as a formal mathematical problem. And so I think this is what the problem was in that case. It's the same problem that there was with the contact tracing apps, that people viewed it as a purely technical problem where you just could almost mechanically apply a mathematical model. That's my understanding of what they did wrong. I don't think it was something special about the COVID pandemic. That probably, if they tried the same thing, the point is they weren't taking into account that American society is very different from Wuhan, and you can't use the shape of the curve. The shape of the curve in Wuhan as of March did look sort of like exponentially increasing for a while, then plateauing, then exponentially decreasing. It did actually look like that. But the curve in the United States does not look like that, largely because of the political and cultural and behavioral differences between and general lack of social discipline in the United States compared to China, which is a very disciplined country when a crisis occurs. So that type of non-science background they did not take into account. That's my understanding of what went wrong.
Thank you. Any other questions or comments? Okay, in that case, let's thank the speaker again.
Thank you.
We'll resume in 3 minutes at 6:30.
Neil, I just want to say that you brought old memories again. I mean, 20 years old memories are really, I'm very happy.
Do you remember all those? Do you remember when we went to see Rambo?
Yeah, I know.
Do you remember the concert you took?
Yes.
Yeah. It was the longest concert I've ever attended,
That's
but
common.
probably the best one too.
Kanika, do you see Professor Busbert? I'm not
I
able
don't
to see.
see him searching.
So let me know if you see him. But then I will make it. I'm not able to see him.
Yeah, I don't see him.
Hi, anyone has Professor Goosebump? He seemed to be not here.
No, Shauli, I don't see him.
Yeah, I also don't see him, and I have not got any email from him. So let me say, let me try to contact him.
Shauli, are you there?
Kanika, yes. Is he there?
Can you add him as a co-host?
Yeah, I'll just do it. Everyone can share. I have anyway made the settings.
Professor Byrne, did you want to share your slides? So we just check if it's working.
Yeah, I tried to log in several times and I was not able to log in.
Okay.
That's the reason why I'm late.
No problem.
You're not sharing the right thing.
Oh. This is,
Yeah.
Yeah, we can see the screen. You could try full screen also.
screen.
Otherwise, we can continue with this. Yeah, this is good. Okay, so are you ready to start, sir?
Yes.
Okay, so it's a great pleasure to welcome Professor Bruce Byrne, the great scholar of Ramanujan. Today, he'll talk to us about balanced derivatives, identities, and bounds for trigonometric sums and Bessel series.
Okay. Thank you very much for the introduction. I apologize. I tried to log in for about 10 or 15 minutes and only just succeeded right now. So this is joint work with Martina Facina, who is a postdoc at the University of Vienna, Sun Kim, who is on the faculty at Hunbuk University in Korea, and Alexander Zaharescu, my colleague at the University of Illinois. So let me show you some pictures of my co-authors. This is Facina. This is Sun Kim. And this is Alexander Zaharescu. Picture is a little bit old. I'll have another picture of him later. I'd first like to express my thoughts for the millions of people who have been suffering from economic difficulties, serious illness, and death due to COVID-19. Probably most of you in the audience have had friends or family suffering from the COVID virus. This is one of the 4 photographs that we have of Ramanujan. It's the most famous one that was procured from Janaki, Ramanujan's widow, in 1936 by Chandrasekhar for the purpose of putting this photo in Hardy's book, Ramanujan. If you'll recall that book, the passport stamps do not appear in that picture. They were removed. Ramanujan had a strong interest in sums of squares, so I would like to begin with sums of squares and the famous circle problem. And then I will go to the divisor problem, and again, a contribution that Ramanujan made to solving the Dirichlet divisor problem. And then the methods that we use to examine these 2 formulas of Ramanujan for the circle and divisor problem, we used for finding identities for trigonometric sums and also estimates for trigonometric sums. So the last part is work in process. And to do this work, we introduced the definition or the concept of a balanced derivative. So I'll like to also talk about that. Okay, so this is one of the first entries from Ramanujan's first letter to Hardy. It's not exactly the problem on sums of squares that I will discuss, but it indicates Ramanujan's interest in sums of squares. So 1, 2, 4, 5, 8, 9, 10, 13, etc. are the either themselves squares or can be expressed as a sum of two squares. And Ramanujan says the number of such numbers greater than a and less than b is equal to this integral here. K is 0.764. Theta of x is very small when compared with the previous integral. Note there is a slight error here, it's just a misprint. The theta of x, of course, should be theta of b. Well, this is really a remarkable result. So this is what Hardy had to say of it in his book or in the collected papers of Ramanujan. The dominant term, that is kb log b to the -1/2 in Ramanujan's notation, was first obtained by Landau in 1908. Ramanujan had none of Landau's weapons at his command. It is sufficiently marvelous that he should have even dreamt of problems such as these problems, which it has taken the finest mathematicians in Europe 100 years to solve. So this really is a remarkable achievement. He had none of the background to ever think about such problems, and then to actually not only think of them, to actually obtain a result on the number of such squares. So here is a picture of Hardy and Littlewood. It turns out that there is a page in Ramanujan's second notebook in which he indicates this result, but you see here it's very, very vague. In this representation for C, he does not fill in what's in the parentheses. I've copied it as closely as I could from the second notebook. And then in the third notebook, he actually gives a proof of this. So it says page 350. The third notebook has only 33 pages, but in the Tata Institute's publication of the notebooks, the second and the third notebook are in the same volume. So the third notebook then continues on with the pagination of the second volume. So here he gives the exact value of K. So here note R runs through the primes of the form of 4n plus 3. And surprisingly, he sketches a proof of his claim in the third notebook. I might remark that of the 3,200 approximately claims in his three notebooks, there are only a handful in which he indicates any kind of a proof. And this is really the only proof in the entire three notebooks that's actually given by Ramanujan. So there's more space devoted to this than any other argument or proof in his notebooks. I don't think the third notebook was available to Hardy and Watson. Watson's handwritten personal copy of the notebooks, I don't think contains the third notebook. Well, that's not exactly that's not the problem I want to discuss. I want to discuss the famous circle problem. So R2 of n is the number of representations of n as a sum of two squares. So different signs and different orders of the summands yield distinct representations. So here we have 5 is plus or minus 2 squared plus or minus 1 squared. Of course, we can invert the order of the summands, and you see that R2 of 5 is therefore 8. Now, each of these representations of n as a sum of two squares can be associated with a lattice point in the plane. For example, if you look at 5 equals minus 2 squared plus 1 squared, we can associate that with minus 2, 1. And then each lattice point can be associated with a unit square. It doesn't make any difference which of the 4 squares we take, but we should be consistent. So let's take the square such that the lattice point is in the southwest corner. So numerically, the number of representations as a sum of two squares, where n is less than or equal to x, is equal to the number of squares such that the southwest vertice of the square is within a circle of radius square root x. So here in this diagram, we have colored red all of the squares associated with lattice points within the circle of radius square root x. Okay, so if we look at the sum of R2 of n, the number of representations of n as the sum of two squares up to x, that will be approximately equal to the area of that circle, pi times square root of x squared. And of course, there will be an error term. We put a prime on the summation to indicate that if x is an integer, we only count a half R2 of x. The reason we do this is that in analytic studies of this sum, this is the sum which naturally arises. And then here, if we count all the lattice points, we're counting the origin as well. So R2 of 0 will be 1 there. So Gauss first examined this problem. He observed that if you take all these red squares, they're all within a circle of radius square root x plus square root 2. And then if you take a circle of radius square root x minus square root 2, that will be completely covered red. Okay, so taking these two inequalities together, we see that R of x is pi x plus an error term, which is big O of square root of x. So the famous Gauss circle problem then asks for what is the optimal upper bound that we can get for P of x as x tends to infinity. Well, this was definitely of interest to Ramanujan and Hardy. And in a paper that Hardy wrote in 1915, or published in 1915, which would have been shortly after Ramanujan arrived in England, Hardy says that the form of this equation, that is this identity, was suggested to me by Mr. S. Ramanujan. I had communicated the analogous formula for d of 1 plus d of 2 up through d of n, where d of n is the number of divisors of n. So J1 is a Bessel function here. Excuse me. So I've always found this statement by Hardy very strange because, you know, he says the form of this equation. Well, if you have the form of the equation, you would really have the identity itself. In other words, you wouldn't say, well, Mr. Hardy, I think there's some representation for the error term involving Bessel functions. So you either would have that representation or not. So I find Hardy's statement a little bit strange. So that series is a starting point often for upper bounds for the error term. As far as I know, this is the best result that we have. It's due to Huxley in 2003. Soundarajan has improved this a bit by replacing the x to the epsilon by quotient of logarithms. So I forgot to mention one thing here, that Hardy showed in this paper that the error term is not big O of x to the 1/4. He had a more precise result, which I will actually further discuss here in just a moment. So in that paper, Hardy gives this identity, which he says is due to Ramanujan. And it's a really beautiful identity. It's not difficult to prove, but note you get from the left to the right-hand side by just interchanging the A and the B. Now, if we differentiate this with respect to B, let A tend to 0, replace 2 by square root B by S, and use analytic continuation, and we get this identity for the real part of S positive. And this is actually the key identity in Hardy's proof that the error term is omega plus or minus x to the 1/4. So I won't define the omega symbol here. Probably most of you know it, but I just want to emphasize that the error term then is not big O of x to the 1/4. Now, actually, Hardy had another proof of this identity as well. He actually gives then 2 proofs in his paper. And here is the exact reference of the paper. So the conjecture is that Hardy's result is actually the closest to the actual order of the error term. In other words, most mathematicians feel that the error term is big O of x to the 1/4 plus epsilon for every epsilon greater than 0. Okay, I want to get to an identity of Ramanujan involving R2 of n. So first, let me recall an identity for R2 of n, which is often proved in, of course, in elementary number theory. So I'm going to use that identity in the summatory function here. But I'm going to write this sum in this way. So you can easily see this is just an equivalent way of writing R2 of n. And then we'll write n as the product dj for a divisor d of n. So we can think of this sum as the sum over all products dj less than or equal to x. So we'll sum on j first, and the sum on j first will be square brackets of x over d, where this is the greatest integer function. So we have this representation, an elementary representation for our summatory function. Now there's an identity involving R2 of n. It's found in a one-page manuscript published with Ramanujan's Lost Notebook. It's just one page, and it's page 335 in the Tata Institute's publication of the Lost Notebook. So here actually is the page with the two formulas for the R2 of n problem and also for the divisor problem. I'll give these identities in more detail. So this is the first one. So J1 of x is the Bessel function, just as we had before. So we have another parameter theta, and these Bessel functions are the same kind of Bessel functions that we had in the Hardy-Ramanujan formula with which I mentioned a few moments ago. So this was first proved by Sun Kim, Zaharescu, and myself in this paper in 2013. Here's a picture of Sun Kim at her PhD graduation about 10 years ago. She actually had two advisors. Kevin Ford was also an advisor. She has the ability of being able to do research in various areas of mathematics. She can switch over from one to another quite easily. Okay, so here is the identity, and here I'm saying that Zaharescu and I first proved this in 2006. So you might ask, well, why did I say that the identity of Ramanujan was first proved by Sun Kim, Zaharescu, and myself in 2013? Well, if you look at this closely, here we're summing an m first and then n. In Ramanujan's identity, we're summing on n first and then on m. So it turns out that it was easier for Zaharescu and I to prove the identity with the order of summation reversed from what Ramanujan had. And to prove the identity in the other direction, for which Ramanujan stated the order of summation, we couldn't use our ideas. So in other words, we had to use completely different ideas to prove the identity with the order of summation reversed. So let me just say a few words about this identity. If you let theta to be a quarter, then the left-hand side reduces to this, and this is exactly the sum which I gave you a few minutes ago that can be derived in an elementary manner. And again, note that those Bessel functions are the same as in the Hardy-Ramanujan formula. Of course, the arguments are different. So the big question is, can we use this extra parameter theta to attack the circle problem? So I have the feeling, but of course I have no proof of my feeling, that Ramanujan actually derived this formula to work on the circle problem. but I've never been able to use this formula in any way at all to attack the circle problem. So I'm afraid it's just a guess, and I really don't know, but I think Ramanujan probably had the circle problem in mind when he proved this formula. Okay, now let me go to the Dirichlet divisor problem and another entry or statement from Ramanujan's first letter to Hardy. So he says, let us take the number of divisors of the natural numbers, 1, 2, 2, 3, 2, 4, etc. And he said the sum of such numbers up to n, this is the way he writes it, is equal to this main term plus 1/2 the number of divisors of n. This is much too optimistic. That is this error term here. Gamma is Euler's constant. Well, first of all, if d of n is the number of positive divisors of n, cap d of x is our summatory function, with the prime having the same meaning as before. Namely, if x is an integer, we'll only count a half d of x. Okay, now we use the same kind of elementary argument as I did a few moments ago. We can write d of x, of course, in this form as the sum of ones over all divisors of n. You write n as the product dj and sum over all pairs dj, the product being less than or equal to x. You sum on j first, and then you get this elementary formula for the summatory function d of x. Yeah. Okay, you can look at this problem as a lattice point problem. So each divisor of n is uniquely associated with the lattice point dj. So this would be in the first quadrant, and it would be under a hyperbola, say ab equals x. So d of x is equal then to the number of lattice points in the first quadrant on this hyperbola. So the Dirichlet divisor problem is equivalent. That is, we want to know what that error term is, for which Ramanujan had a very optimistic view. It's equivalent to the problem of estimating the number of lattice points on a certain hyperbola. So Dirichlet and probably Ramanujan argued in this way to get that formula, which I just mentioned that Ramanujan sent to Hardy in his first letter. We take the region under the hyperbola AB equals x and divide it into three regions. So you first estimate the number of terms or lattice points in regions 1 and 2, and then in regions 1 and 3, which of course would be the same. And then, since we counted the number of lattice points in this square twice, we subtract off the number of lattice points in this square. So that's the main idea. So then we get that the d of x is equal to this. This is what Ramanujan had, but he said had n instead of x. I put this 1/4 in just because in analytic examinations of the Dirichlet divisor problem, this 1/4 just naturally arises. Of course, it can be put in the error term, delta of x. So Dirichlet showed that the error term is big O of square root of x as x tends to infinity. Finding the correct order, the optimal order for the error term is called the Dirichlet divisor problem. And there is an analogous identity to the Hardy-Ramanujan identity for R2 of n. So it involves other Bessel functions. So just y is defined in terms of the ordinary Bessel function this way, and k in this way. And so then one can prove, as Voronoi did, this representation for the error term in terms of these Bessel functions y and k. So again, I1 would be minus y1 of this argument at minus 2 over pi times the k Bessel function. And just like we did for the Gauss circle problem, the asymptotic formulas for the Bessel functions are keys to estimating this sum on the right-hand side in order to get bounds for the error term better than what Dirichlet got. So Voronoi proved in 1904 that delta of x is big O of x to the 1/3, log x as x tends to infinity. And again, the current result, the best result, as far as I know, is due to Huxley. So if any listeners know of a better result, please let me know. As I mentioned, Soundararajan has replaced the x to the epsilon by a quotient of logarithmic terms. Well, there's an identity involving d of n on this one-page manuscript that I just showed you. And this is the formula involving d of n. So instead of a sine, we have a cosine. Again, we have an extra parameter. And then we have these I Bessel functions, or these linear combinations of y and k that we had before. Okay, so let me make a few comments. If we let theta to be 0, then the left-hand side just reduces to this. And this is that elementary formula that I proved about 2 minutes ago. Okay, again, I remind you that this is Voronoj's formula, and the Bessel functions are the same ones as appear in Ramanujan's formula. So the first theorem we proved is as follows. If we invert the order of summation and assume convergence for one value of theta, then we can prove the identity for all values of theta. So this was our first result. So again, this is due to Sun Kim, Zareski, and myself in another paper. But I emphasize we had this strange hypothesis. We had to assume convergence for one value of theta, and we had reversed the order of summation. Well, it seems like now I'm going off in another direction. You might, but I'll come back to this problem. So I want to go make a diversion for just a second here. So in Watson's retiring address as president of the London Mathematical Society in 1936, he gave a lecture entitled, as I given it here, and this is the published version of his lecture. So he calls this the final problem, an account of the Mach theta functions. And the reason he does this is that in Ramanujan's last letter to Hardy, the only letter that he wrote to Hardy after he returned to India, he discusses Mach theta functions. So, and then in some sense, the Mach theta functions are what was thought of at that time, or probably is true, the last creative problem or problems that Ramanujan worked on. So Watson borrowed this title from a famous Sherlock Holmes story, The Adventure of the Final Problem. This is perhaps the most famous, and it's also the last of the Sherlock Holmes stories. And moreover, Sherlock Holmes' famous sidekick in the stories is Dr. Watson. So a couple of reasons for why Watson chose this as the title of his valedictory address, or as the title of his paper. Well, it took us a long time to actually solve the problem or prove the identity as Ramanujan had written it. So this is the final problem for Andrews and myself when we edited the notebooks. So in our fifth and last volume of the notebooks, or our editing of Ramanujan's notebooks, we actually only proved the identity with the order of summation reversed. So this was our final problem. But fortunately, we did solve it just recently. So Junxian Li, graduate student under Zarescu and myself, we finally proved this identity, and we published it in the Journal of the London Mathematical Society, where Watson had published this paper. So if you want just a overview of the problem without any proofs, this expository version of our paper was just published within the past month, actually, in a volume dedicated to George Andrews on his 80th birthday. So here is a picture of Junxian Li and Zarescu. Junxian Li is currently a postdoc at the Max Planck Institute in Germany. Okay, let me just make a few comments on our proof. So the series on the right-hand side does not converge absolutely. And we have to use asymptotic formulas for the Bessel functions in order to examine or prove this result. And here's probably the key idea. So in the identity, in the denominators, are these square roots. And there's, so what we do is to, in each case, we introduce two complex variables. So there are actually two complex variables. So instead of having n plus theta to the square root, we're going to replace the square root by s, and also we're going to replace the square root of n plus 1 minus theta, that power, by w. So we're going to examine the series in these more general settings of complex variables s and w. And then later we'll use analytic continuation. So we can show that the series actually converges uniformly with respect to theta in any compact subinterval of 0, 1 under these conditions. So I just want to emphasize that here we have a lower bound of 25, 26 if x is not an integer, and 5, 6 if x is not an integer. So if I just took square roots here, of course, on the left-hand side of this inequality, we would have a half and a half. So you see, we have bettered our results, so to speak, or our convergence by, augmenting the domain of convergence here. So this is the key to get this improvement on the radicals that we have in the original formula. Okay, to do this, as it just indicates here, we have to separate the cases when x is an integer and x not an integer. And then we have to divide the intervals in each case into intervals with small and large values of m and n, as one often does in estimating trigonometric sums. So this is the second major idea, or involving a series of ideas to determine what these intervals should be in order to show the uniform convergence. Okay, then after we do that, we note that there are discontinuities on both sides of the identity that we want to prove. We can get rid of them by multiplying both sides by sine squared of pi theta. Then we just isolate the Bessel functions on the right-hand side. And then we calculate the Fourier series on both sides of the amended identity that we want to prove, and show that the Fourier series are identical. Now on the left-hand side, it's not too difficult, it's quite easy to calculate the Fourier series. But on the right-hand side, where there's a double sum of Bessel functions, it's much more difficult to actually calculate the Fourier series. But one can do this indeed the Fourier series are identical. And because then both sides of our amended identity are continuous, we can appeal to the uniqueness theorem for Fourier series to conclude that the functions are identical and conclude the proof. So that's a sketch of our proof of the last identity from the, I think I said Tata Institute is really the Neurosa publication of the Lost Notebook, and all the other fragments and unpublished papers that Ramanujan left us at his death. Okay, now I'd like to discuss some work on trigonometric sums that actually arose out of our ideas in proving these two formulas. So some of the work I will now mention is in this paper we published in Krella in 2013, and the other parts will be in a paper that we just submitted for publication a few weeks ago. So here is one of the sums that we examine. So we have two variables now, sigma and theta. So sigma and theta will be between 0 and 1. Okay, we've made a conjecture about this sum. Namely, for every epsilon greater than 0 as x tends to infinity, we conjecture that this sum is omega plus or minus x to the 5/4. Okay, so let me just give a very rough idea as to how you might think of this. So for the circle problem, remember it's x to the 1/4. So note here that we have an m and an n in our sum. So we're, of course, then increasing, so to speak, the values of this sum. So if for each variable we increase by square root, then you would guess, well, then the error term should be about x to the 5/4, or this should be an omega result. Well, that's a very rough reasoning. We have much better reasoning for this, but we can't prove it then. However, we can prove a result, a big O estimate. So this actually is a theorem that this sum is big O of x to the 1/4 plus epsilon, that for every epsilon greater than 0 as x tends to infinity. Okay, so we have these trivial decimal expansions. So this result would be analogous to Voronoi result for the sum of d of n. Remember that he showed the summatory functions b of x to the 1/3 as x tends to infinity. So, roughly speaking, we've added a square root for each of those two variables then. And we would guess, like we have for the circle problem, that probably this sum is big O of x to the 5/4 plus epsilon for every epsilon greater than 0 as x tends to infinity. So just analogous to Hardy's result, we think that this is probably the order of magnitude of the error term. So we've examined a few other sums of this type, and we have omega conjectures. In each case, we don't have any theorems, but we do have big O results for these. I thought I would just give you one special case of this. If you take theta and sigma to be 1/4, okay, then this is the sign that you have here for each. Both the signs are equal to this. So this is just trivial. So you substitute these sign values in. So I've now indicated here what the arguments of theta and sigma are. So the only contributions are from odd indices. So I've replaced the m and n by 2j plus 1 and 2k plus 1 here. Okay, so this is somewhat of a rather interesting lattice point problem. We are counting lattice points under a hyperbola, but we require both of the coordinates to be odd, and we put a weight on these lattice points, the weight being the lattice points themselves, and then the power of -1. Of course, for other values of theta and sigma, you can state similar kinds of results. We've also examined sums involving an arbitrary number of signs. So here we have k signs, and here we've put our variables, we put them as rational numbers without really loss of generality here. So in other words, theta, for example, is replaced by a1 over p1. A1 and p1 are relatively prime, etc. Okay, we have a conjecture about these sums as well. And I've put our conjectures now not in terms of the omega estimates, but in terms of lim sup and lim inf. So we conjecture that the lim sup of the sum divided by x to the 3k minus 1 over 2k is plus infinity, and similarly for the lim inf. So if k is equal to 2, then note that this reduces to 5/4 what we had in the previous conjecture. Okay, so this is a theorem that we have, our big O theorem. So we have this upper bound for the sum as x tends to infinity. Okay, let's just look at what's happening here as we increase the number of variables. So here I have k plus 1 variables, the exponent for k plus 1 variables, here for k variables. Okay, so this is the difference by arithmetic. So you see that if we increase the value of k by 1, we increase the upper bound that we have by a very small amount, big O of 1 over k squared. Now, I'm not saying that, of course, that these are the optimal upper bounds. I'm just indicating that this is what happened, what we have for the theorem that we're able to prove for upper bounds for the sine sums. So we would like to know if we can take partial derivatives. The reason we would like to take partial derivatives is that we want to show uniform convergence, so we don't have to worry about which order that we take our double sum, like we had to worry about when we looked at Ramanujan's two identities on page 335 in the Lost Notebook. So we can take partial derivatives, invert the order of summation if we take balanced partial derivatives. What we're indicating here is that we take the same number of derivatives in sigma and theta. So if we do this, we say the identities that we obtain are balanced. So if we don't take the same number of derivatives for sigma and theta, we have an unbalanced number of derivatives. So if we have an unbalanced number, we're not able to actually carry through our arguments for convergence, for uniform convergence that we have in the balanced case. Yeah. Okay, so to take an example, so here's another sum that we examined and have identities for. So if we take then the partial with respect to sigma k times and theta k times, then we can actually move the partial derivatives inside the summation, and we can do this by the uniform convergence. So here there are actually 4 different quotients of Bessel functions appearing in our identity there. So the key ideas are somewhat the same as in our proof of Ramanujan's final identity. So here note that there are 4 Bessel functions appearing, and when we take derivatives, we get each case the number of Bessel functions is multiplied by 2, etc. So again, what we do is to introduce 2 complex variables, S and W. So before we just had 1 variable, theta, but now we have 2 variables, sigma and theta. Yeah. So the introduction of the complex variables is slightly different, well, not slightly, but it is different from what we had before. Yeah. Okay, sorry, this is actually what I did before. I went backwards here. So again, we assume that these inequalities are satisfied, and we prove the same kinds of results for convergence that we had before. So I emphasize that although we have two complex variables, they are in a different from what we had before. Before we just had one variable and we looked at n plus theta and n plus 1 minus theta. Here, we're looking at n plus theta and n plus sigma to these complex variables. Yeah. So we show that we have uniform convergence with respect to sigma and theta on any compact set in 0, 1 cross 0, 1. Yeah. So here is an identity involving two cosines, product of two cosines. This I Bessel function is the same as we had before. That is the difference between the y and the k Bessel functions. Just might mention that in our proofs, we actually encounter integrals of Bessel functions. So these are common Bessel, these are well-known formulas for j minus a half and j 1/2. And j 3/2 is actually a linear combination of these two. And this is a non-trivial evaluation, but you can evaluate, I call this t 3/2 because we have other kinds of t intervals there in terms of these Bessel functions. So we can get an identity going back to our original sum involving sines here. And in terms of this integral of Bessel functions, or what I called t 3/2, or in terms of the Bessel functions, the I Bessel functions. Okay, and just a couple minutes that I have, I would like to show you some photographs of buildings connected with Ramanujan. So this is the home where actually Ramanujan was born in Erode. And this is the home in Kumbakonam where Ramanujan lived for much of his life. So I was able to see this home in 1984 when Balu accompanied me from Madras or Chennai to Kumbakonam. So I am very grateful for Balu to accompany me to Kumbakonam to see the house that Ramanujan was raised in. It's now been turned into a museum. I've seen the museum, but I'm very pleased that I was able to see the home as Ramanujan actually lived in it. So behind, there's a sort of a porch area behind the bamboo curtains. And the only indication that this was Ramanujan's home came from a photograph of Ramanujan that was clipped from a newspaper and put above the entrance by the family living in the home. So here is one picture of the inside of Ramanujan's home. And note there's some stairs here going up to a small second floor in the home. And here is another picture of the father and his children in the home. And you will recognize Balu talking with the father. Here is a photograph of the high school that Ramanujan attended. You may not be able to recognize, this is Balu talking with two of the teachers at the high school. Here is a room in the high school named after Ramanujan. Here's perhaps a better view of the high school. So thank you, Balu, for taking me on this trip. I will never forget it. It's one of the highlights of my life. Happy birthday. So thank you very much for the invitation.
Thank you very much for a wonderful talk and also sharing the lovely pictures of Kumbakonam and your visit there with Professor Balu. So let's thank the speaker. questions or comments?
Probably, Professor Bruce, but you can probably mention the article in Mass Intelligence, I think, which you wrote immediately after your visit, which would
Yes.
probably give more details.
Yes. Okay. I recommend it. Yes. Thank you very much for that recollection. Yeah.
So just out of curiosity, the family in the last few pictures that you showed, are they in some way the extended family of Ramanujan? Or
I don't think
No, they have no, as far as I know, I think I asked that question. There really is, no family. They're not related in any way to Ramanujan.
okay, thank you. Any other questions or comments? Okay, in that case, let's thank the speaker again.
Thanks very much for the invitation. Yeah.
So we will resume at 8:30 for the next session. Thank you all for being present for this session, and I hope you enjoyed it. Shauli, you had any comments?
Thank you, Kanika, for chairing this session, and let us thank all the speakers of this session. And we will meet in 1 hour's time.